And at a high level, phototherapy, in the simplest form, is a way to treat certain disease states with light. Benefits of this, just to name a few, it's pretty versatile. There's plenty of various disease states that can be treated with different wavelengths of light. It's generally not invasive, depending on how deep in the body you need to go. It can be very targeted. You can treat the whole body. You can treat just certain areas that may be affected. And generally, in most cases, there's very little to zero side effects, which is, contrary to, say, a pharmaceutical or surgery. Giving a couple examples of treatment types. Neonatal jaundice, there's been a blue light treatment. I think it's like that. It's been around for decades. But it really is kind of a benchmark of treatment for that. You see that in a lot of babies. And that basically takes that wavelength of light, transfers the bile into something soluble so that it can pass through and eliminate the need for the condition brain damage. Various types of skin type of treatments can be done. Eczema, vitiligo. Wound healing is another one, similar to infection. And certainly certain types of cancer treatment can be used for phototherapy. So as a designer or an engineer, if you were to design a device for phototherapy, there's certainly some basic fundamentals you want to consider. The first one is wavelength. So, to kind of set an example, if I'm treating jaundice, my wavelength, say, needs to be 640. And so if you're developing a device and you're trying to spec out probably an LED, that's the way most of this equipment is moving towards, there may not be an LED on the market that's 640. You may find one that's 630 to 650. So with that being said, what you need to consider is there any adverse effects? If that disease state is well treated within that narrow wavelength, what are the ramifications of any if I go plus or minus that? 30 to 50, are there any adverse effects? Do I have to have the treatment go longer? Certainly things to think about. Surface area coverage is another good one. I gave the example of something like vitiligo. You may need to treat the whole body and put them in some kind of booth that you can say like a tanning booth, or if I'm doing some kind of cancer treatment, I may want to pinpoint exact cells. Those are all things that you need to think about. Absorption rate and heat transfer kind of go hand in hand. I think for the most part, a lot of challenges we get with clients and customers coming to us, something they overlook is heat transfer. When you think about LEDs or any kind of light source, you're certainly delivering that light, but you're also producing a lot of heat. And as a rule of thumb, you normally don't want to transmit that heat from the source to the patient. So it's very advantageous to think early of how you're going to mitigate that heat and keep it at the source, not at the patient level. And that goes along with treatment duration. If I have a rule of thumb, if I have a higher intensity to reduce my duration so that the patient can get out of the dosage time sooner than later, I'm probably going to produce more heat. So all three of those have to have a delicate balance to work out. Just a quick side note, the top picture on the right. That's kind of an R&D project, and it's interesting because it incorporates some of what the considerations I talked about, and another one that kind of goes to show that you can't always think of everything. So the quick background on that is that's a condition called ischemic reperfusion injury. So a lot of times in a neonate, they may have a cardiac or stroke event, and when that happens, oxygen is rushed to the brain, cause brain damage or death. And so what the research out there says, if you kind of bombard those cells with a certain wavelength of light, you can slow down that regression of oxygen, thus preventing brain damage. The interesting challenge with this is, you can imagine, if I need to take light through the skull and into the brain, what are my challenges going to be? I've got quite a bit of medium to go through. I've got different medium. I've got skin, I've got the skull, and I've got whatever in between to reach the brain. And so, as engineers, we were able to develop a system that could do that, but there was one fundamental thing we forgot earlier in the process. It sounds kind of trivial, but it turned out to be something we had to kind of iterate and move back, is some babies are born with hair, right? So if you think about it, you design this thing, you forgot about the hair, and now you got to go back and kind of revise, redesign to accommodate. And so we were able to do that to a certain extent, but the protocol ended up being, in order to use this as in clinical trials now, part of the operation is sometimes you may just have to shake that. It kind of worked out, but it just goes to show you that even if you think of everything,